Until now, we have looked at algorithms, both exact as well as approximate, that solve marginal inference tasks in graphical models. Today, we will look at algorithms that solve so-called optimization problems defined over graphical models, specifically two tasks, MPE and MAP inference. Here is what we'll cover in the lecture today. We will look at the definition of MPE, or most probable explanation. To recap, MPE is defined as the tuple or the assignment of values to all variables in the graphical model that has the highest probability. We'll also look at the definition of map inference or maximum-a-posteriori inference, and we'll see that MPE is a special case of map inference. The definition of map inference is as follows. You are given a subset of variables y in the graphical model, and you are asked to find an assignment of values to this subset of variables such that the probability is maximized. As you can imagine, if the set y includes all the non-evidence variables in the graphical model, then MPE is nothing but map inference. Therefore, MPE is a special case of map. We will then look at two types of algorithms for solving MPE as well as MAP. The first type of algorithms, as you can imagine, are exact inference algorithms, and the second type of algorithms are approximate inference algorithms. This slide shows the running example that we will use to illustrate the definitions of MPE and map tasks. We'll also use this example to demonstrate algorithms for solving map as well as MPE. On the slide, we are given a Bayesian network that describes our prior or background knowledge about cheating at exams in the UTD CS population. Specifically, let's say in the machine learning course. I'm sure that since this is a graphical models course, and most of you have already passed the machine learning course, most of you are not cheaters. So we're not going to worry about this class right now. We're only going to worry about the machine learning course. The Bayesian network has 5 variables: S, C, T1, T2, and A. S denotes the sex of the person, C whether the person cheats or not, and T1 and T2 denote the two tests that the professor uses, let's say, to determine whether the student cheats or not. For instance, the test T1 may be based on using video recording of the class taking a particular exam, let's say the midterm or the final. And test T2 might be some external tool such as MOS, which finds similarity between two submitted assignments. Finally, A denotes the agreement between the two tests. The CPTs given on the slide define the conditional probability tables that are associated with the variables in the directed acyclic graph. Let us try to dive into the CPTs and see what kind of knowledge they represent. The CPT at S says that the probability that a randomly chosen student in the class is male is 55%, while the probability that the student is a female is 45%. The CPT at C says that the probability of a male student cheating is 5%, while that of a female student cheating is 1%. So in a way, males are more likely to cheat as compared to females. Don't get offended by it. Clearly, our Bayesian network is gender biased, but that's okay. As machine learners, we let the data speak and worry about biases later on. Test T1 is general neutral in the sense that it only depends on whether the student cheats or not. Test T2 is not gender neutral in the sense that it depends on whether the student cheats or not, as well as whether the student is a male or a female student. Finally, the CPT at A is a deterministic CPT. What I mean is that all probabilities in the CPT are either a 1 or a 0. If you look carefully at the CPT associated with A, you can see that the CPT models the constraint that if T1 and T2 agree, which means that T1 and T2 are either both positive or both negative, then A has the value S, yes. Otherwise, A has the value no. Now let me test whether you understand the definitions of MPE and MAP. To recap, MPE is defined as the most likely assignment to all non-evidence variables given evidence, while MAP is defined as most likely assignment to a subset of non-evidence variables given evidence. So in the Bayesian network given on the previous slide, let's say that we have evidence where we know that a person has taken a test and the test administrator says that the two tests agree, which means that we have evidence that the value of A is true. Let us say that our query now is to find a most likely instantiation or a most likely assignment of sex and cheating given that A is equal to true. Can you tell me now whether this is an instance of the MAP problem or an MPE problem? I'll give you a minute to think about it. Now that the minute is over, and since this is an online lecture, a minute only lasts for about 15 seconds. If your answer was MAP inference, you are correct. If your answer was MPE inference, you are incorrect. This is because this problem requires an assignment to only 2 of the 4 non-evidence variables. And since we need an assignment on a subset, it's an instance of a MAP problem as compared to an instance of the MPE problem. If you compute a joint probability distribution over the 2 variables sex and cheating given evidence by performing marginal probability inference over the model, then you'll figure out that the answer in this case is that sex is equal to male and cheating is equal to no. So this is the most likely configuration given that the 2 tests agree. Let me now highlight some important properties, specifically similarities and differences between MPE and MAP inference. The first property I want to mention is that MPE is a special case of MAP, and the proof to this is obvious. Given a MAP inference problem, if the subset Y, and I'll often refer to the subset Y, the MAP inference problem, as the set of MAP variables, and if that subset Y equals the set of non-evidence variables, then MAP is equivalent to MPE. The second property that I want to highlight is that MPE is NP-hard, while computing MAP is NP-PP hard. Thus, from a purely theoretical point of view, MAP is a much harder problem than MPE. Intuitively, MAP involves computing a marginal probability distribution over the MAP variables, which is a type of sum product problem, and then maximizing over that marginal distribution, which is nothing but a maximization problem. In other words, if you think about MAP inference, map is nothing but an instance of a max sum product problem, while MPE is a special case in the sense that it's an instance of a max product problem where you don't have to compute the sum. Thus, intuitively, it is obvious that since you have an extra operation which is nothing but the summation operation, map is a harder task as compared to MPE. A third distinction, and this is an important one that I want to highlight, is that MPE projected on the map variables. So if you give me an MPE assignment, and if I project the assignment over the map variables, it will not yield the correct solution to the map problem. Even though this is obvious to many researchers, it is often tempting to do this in practice. This is because MPE is an easier problem, and thus we can use MPE algorithms if we project the MPE assignment on the map tuple to solve the map problem. Unfortunately, you have to be careful, as I said, because it will often yield incorrect results. So coming back to a running example, let us try this. So given A equals yes, you can verify that the MPE tuple is S equals female, C equals no, and both T1 and T2 are negative. If we project this tuple over S, C, T1 and T2 on the map variables, which are nothing but S and C, we get the tuple S equals female and C equals no. Unfortunately, this is incorrect because the map tuple, or I should say the correct map tuple, is S equals male and C equals no. And again, you can verify this. A final point I want to make is that we'll distinguish between MPE and map probabilities and MPE and map tuples or instantiations or assignments. From an optimization perspective, probabilities give the optimal value of the objective function, while tuples or instantiations give the optimal assignment to the variables of interest in the optimization problem. Next, we'll discuss exact inference algorithms for solving the MPE task. We will look at two algorithms, one based on bucket elimination and the second based on branch and bound search. Branch and bound search is a new algorithm, and therefore we will go slowly over it. While bucket elimination we have discussed at length, and therefore I'll breeze through this algorithm. Frankly speaking, the bucket elimination algorithm for computing the MPE tuple as well as the MPE probabilities is quite easy to describe. In particular, to compute the MPE probability, all we have to do is replace the sum out operation in the bucket elimination algorithm for computing the marginal probability distribution or for computing the probability of evidence by the max out operation. All other things in the algorithm remain the same. Specifically, things like the complexity guarantee associated with the algorithm, as well as other operations. I will illustrate the max out operation using a factor that is defined over S and C. Suppose that we want to max out the variable S from this factor. You can achieve this by fixing the values of the remaining variables, which in this case is C, and then choosing the maximum value over the possible instantiations of S. As you can see, S has two possible instantiations, male and female. So in order to compute the max out of this function over S. We fix the value of C to S, and we max over S equals male and S equals female. If you look at the function, we get the value 0.05. Then what we do is we fix the value of C to no, and then max over S equals male and S equals female. In this case, we'll have to compute a max between 0.95 and 0.99, and therefore we get a 0.99. Now let us see how the bucket elimination algorithm will operate to compute the MPE value or the MPE probability. As before, we'll use our running example. If you recall, the UTD-CS cheating network. The task here is to compute the MPE probability given evidence A equals true or A equals yes. Again, recall that in the bucket elimination algorithm, we use the primal graph defined over the evidence instantiated network. The primal graph over the non-evidence variables is given on the slide and drawn along the order SC, T1 and T2. As before, what we will do is we'll associate a bucket with each variable in the order. Then we take each function, and remember that we are using evidence instantiated CPTs or factors, and we put each function or each one of these evidence instantiated CPTs in the first bucket along the order that mentions a variable in the function. For example, we put the function, and again the function here is an evidence instantiated CPT, defined over C, S and T2 in the bucket of S. Why do we do that? Because S is the first variable in the function along the order. Similarly, if you consider the function which is defined over C and T1, we put that function in the bucket of C because C occurs before T1 in the order that is given to us. After we have populated the buckets, we process the buckets from the first variable in the order to the last, right? So on the slide, we will go from top to bottom. To process a bucket, we multiply all functions in the bucket and max out the variable associated with the bucket. This will yield a function that is defined over all the non-bucket variables. And we put that function in the appropriate bucket. By appropriate bucket, I mean the same process as before. We put the function in the highest ordered variable appearing in the function. Or I should say, we put the function in the bucket of the highest ordered variable appearing in the function. In our running example, when we process the bucket of S, for instance, we get a function that is defined over C and T2. And we put that function in the bucket of C. At bucket of C, we multiply the functions defined over C and T1 and C and T2. When we do that, we get a function which is defined over C, T1 and T2. From this function, we max out C, and this will yield a function that is defined over T1 and T2. We put this function in the appropriate bucket, which is nothing but the bucket defined over T1 because T1 is ordered before T2. So we continue this process, and at the end, when the last bucket is processed, we will get the MPE probability. Now the correctness of this algorithm can be established by substituting the sum out operation by the max out operation in an original proof that established the correctness of bucket elimination for computing probability of evidence. So the proof is fairly simple. There's a caveat that I want to mention, and this is something that I also mentioned when we looked at the bucket elimination algorithm for computing probability of evidence. If while processing a bucket you get a function that has no variables in it, you might have a question on where should I put that function. And the answer is that you put that function in the last bucket. Okay. Another way of saying this is that if you have a bucket and if you process the bucket you get a number, then you collect all such numbers at the end, including the number that you get from the last bucket, right? And then multiply all of these numbers. And when after you multiply all of these numbers, you'll get the MPE probability, right? So the MPE probability is the product of all numbers, right? Or all functions that are defined over no variable. If you want to recover the MPE tuple, in optimization terms, find the optimal assignment to the problem variables rather than the optimal value of the objective function, we have to run a so-called backward pass. What I'm going to do now is describe how this backward pass works. At each bucket, we find an assignment to the bucket variable that has the maximum probability given an optimal assignment to odd variables ordered below the bucket. Thus, at the last bucket, which is the bucket of T2, we have a function that is defined over T2. And we find the value of T2 that has the maximum probability. You can run the numbers and verify that the probability is maximized when T2 is negative. So now we set T2 to negative. Remember, we are running the algorithm bottom up, and move to the bucket of T1. At the bucket of T1, we set T2 to negative in all functions that mention T2, multiply the resulting functions to yield a function which is defined over T1. Again, you can verify that if you run the numbers in the new function obtained by setting T2 to negative and multiplying, you will find that the optimal value of T1 is T1 equals negative. At the bucket of C now, since we are running the algorithm bottom up, we know that T1 is negative and T2 is negative. So we set T1 and T2 to negative in each function in the bucket, multiply the resulting functions, and we get a function that is defined over C. In this function, again, if you run the numbers, you can verify that C equals no has the maximum value. So we set C equals no, and we continue this process until all bucket variables are assigned a value. And at the end, we just collect the optimal values at each bucket, and that assignment will give us the MPE tuple. So in summary, to compute the MPE probability or the optimal value of the objective function, we run the bucket elimination algorithm along the elimination order. In the slide, we run the algorithm from top to bottom in order to compute the MPE probability. In order to get the MPE tuple or the optimal solution, we process the buckets from bottom to top after we run the elimination algorithm. Note that this is important. The bottom-up process is correct, and I want to stress this, the bottom-up process that I just described is correct only after the running the elimination algorithm and not before. Okay? Because as you can see that the bottom-up process does not have exponential complexity, right? The exponential complexity for computing the MPE tuple comes from the elimination process and not from the bottom-up pass. The complexity of the max out operation is the same as the sum out operation over the factors. Do you agree? Therefore, the time and space complexity of the bucket elimination algorithm for computing the MPE probability remains the same. What I mean by remains the same is that the same complexity as the probability of evidence task. Thus, time-wise, it is exponential in the width of the order plus 1, and space-wise, it is exponential in the width of the order, and the width of the order is denoted by W. Thus, the best you can do is exponential in tree width plus 1 time-wise and exponential in tree width space-wise. Once the buckets are processed, the bottom-up operation is linear in the number of functions in each bucket. And as such, the bottom-up pass or the backward pass does not contribute to the overall complexity, since the elimination operation or the top-down pass is exponential in width plus 1. Next, what we'll do is we'll discuss search-based algorithms for computing the MPE probability. We will start with the naive algorithm and then move to a more sophisticated algorithm, and that sophisticated algorithm is called branch and bound. The naive algorithm is straightforward, right? And remember, like, this is the same that we did for marginal inference or for computing probability of evidence, where we first discussed elimination based algorithms for solving the problem, and then we looked at search based algorithms for solving the problem, and then we saw the relationship between the two, right? So right now I have already presented the uh, elimination based algorithm, and we are looking at the search based algorithm, right? So the naive search based algorithm is very straightforward. You use an OR tree over all variables along a particular order. So on the slide you are shown an OR tree, a full OR tree over the order S, C, T1 and T2, right? So S is the root node, followed by C, followed by T1 and followed by T2. You can use this OR tree to compute the MPE probability as follows. All you have to do is at each leaf node, you compute the probability of that assignment by taking a product of the appropriate factors. So you project the assignment on the factors, on each factor, and take the product of the number that you get from each factor. So now each leaf node, if you do that, will be associated with a value, right? And this is the probability of the assignment along the path from the leaf node to the root node in the OR tree. Once you do that, the MPE probability is the leaf node with the highest value. Agree? And then the MPE tuple will be the assignment along the path from the root to the leaf, right? And that particular leaf having the highest probability, I should say. Unfortunately, what will happen is that this algorithm is impractical. And actually, it's very easy to see why this algorithm is impractical. The time complexity of this algorithm is exponential in the number of variables, even though the space complexity is linear, right? If you explore the OR search tree using depth first search, then you only have to maintain O of n states in memory, and therefore the space complexity is linear. Okay? But since the time complexity is exponential, we need to somehow improve this algorithm. Otherwise, this algorithm will be not be useful in practice. The branch and bound algorithm improves over the naive or depth first search exploration using a pruning technique. And the pruning technique, I should say, works as follows. At each node, while performing depth first search, you calculate an upper bound over the remaining problem. And at the same time, you maintain a current best solution. So now if the upper bound that you have computed is smaller than the current best solution, then you can safely prune the node, because the node will not appear in any of the optimal solutions. For example, let us explore the OR tree from left to right, right? If you do that, then you will begin with a solution that has probability of 0.3344, which is the leftmost leaf node on the tree shown on the slide. Now, on this tree, consider the red node which is labeled by T1. Okay? Let us say that we have a method which tells us that the upper bound when T1 is assigned the value positive is 0.0209. Remember, we are interested in the maximization problem, right? The optimization problem is not a minimization problem, it's a maximization problem, right? So the maximum value of the leaf node is what we want. Now, since the upper bound is telling us that the maximum you can get if you set T1 to positive is 0.209, what we can do now is we can safely prune the subtree that is rooted at T1 equals positive, right? Which is now shown by an X under the subtree which is rooted at T1 equals positive. And the red is, and I should say like the color of the X or the color of the cross is red. Similarly, consider the blue node which is now labeled by C. When C is assigned the value yes instead of no, the upper bound is 0.0176. And if you now look at that node, you can see that we can even prune this node. Why? Because the upper bound is smaller than our current best solution, which is 0.3344. Therefore, we can prune the subtree which is rooted at C equals yes. Continuing further, we can prune all subtrees, and you can verify this, marked with a cross. The optimal solution is shown in bold, and the optimal value is 0.33858. As we can see, if we compare this prune tree with the full OR tree given on the previous slide, the prune tree is much smaller. Okay, and that's the utility of pruning, right? And that's why branch and bound is a sophisticated algorithm, because instead of exploring the OR space naively, what you're trying to do is be more clever about it by using a pruning technique. And the pruning technique requires an upper bound, right? So what we'll do next is we will look at an upper bounding technique. Okay. So one final point I want to mention is that the performance of this algorithm is highly dependent on the quality of the upper bound. And higher the, or I should say lower the upper bound, right, the more the pruning. And if you have a method, if you have, let's say, two methods, one method gives smaller upper bounds than the other methods consistently, then branch and bound with pruning method 1 will be much better in terms of number of nodes explored as compared to the branch and bound algorithm that uses pruning method 2. Okay, so if you want to improve any branch and bound algorithm for that matter that can be used to compute the value of a maximization problem, the easiest way to improve the quality of the branch and bound algorithm in the terms of number of nodes explored is to improve the quality of the upper bound. Okay, so that's the main issue, and that's what we will address next. So there is a simple upper bounding idea that we can use. And the main idea here is to decompose the max product problem into two or more max product problems, independently compute exact answers for each one of those independent problems, and then take the product of these independently computed answers. We can guarantee now that the product of these exact answers on these independent problems is an upper bound on the original problem. Okay? And this is the idea behind mini buckets, which was a scheme that was introduced by Rina Dechter and Irina Reisch in the 1990s, and it appears as a Journal of ACM article, I believe, in 2003. So what does this algorithm do? Okay, or what does this mini bucket idea do? So if you recall, the main issue with the bucket elimination algorithm is that it's exponential in the tree width, right? And this exponential complexity is the reason that this algorithm is impractical. And where does the exponential complexity of the algorithm comes from? The exponential complexity actually comes from the product operation inside each bucket. Remember, like the sum out operation once you have computed product is just linear in the size of the product function, right? So the product function is the reason for the exponential complexity. In particular, what will happen is that the product function will be defined over a large number of variables, and since the size of the product function is going to be exponential in the size of a large number of variables, it will be impractical. So to bound the complexity of computation, what we can do is split the functions in the bucket into several groups such that the complexity of each group is bounded. And the way we can ensure that the complexity of each group is bounded is by saying that the number of variables appearing in each group is bounded by a constant. Okay? So the size of the function will be exponential in a constant, which is still a constant. So once we have divided the functions into groups, what we can now do is we can perform max product in each group and return the product over the max products that you have just computed, right? So each one of these independent components, you compute the max product, you get a number, and then finally what you do is you return a product of all these independent numbers. For instance, as shown on the slide, let's say you have a bucket containing n functions from phi1 to phi n. We can split this bucket into two mini buckets, where the first mini bucket has r functions and the second mini bucket has the remaining n minus r functions, right? So the first mini bucket has functions phi1 to phi r, and the second mini bucket has functions phi r plus 1 to phi n. Okay? After we do this, we compute h1, which is the optimal max product value over the first mini bucket. And if we ensure that the product of phi1 to phi r, right, so all the functions from phi1 to phi r, the number of variables in that product function is bounded by a constant, we can do this easily. Agree? Right? Because the overall complexity of computing the product will be exponential in a constant, and if the constant is, let's say, something like 10 or 12, we can easily do that in practice, because if you have just 10 variables in each one of these mini buckets and each variable takes two values, then the size of the product function will be just 2 to the power 10, which is 1024 entries. So after we have computed h1, which is the optimal max product value over the first mini bucket, we compute h2, right? And again, we have to ensure that the number of variables, right, over which the functions phi r plus 1 to phi n are defined, right, or I should more specifically say the product function is defined over, is bounded by a constant. Okay, and then this operation is practical. So we get h1 and h2, and now we can conclude that h1 and h2 is an upper bound on g, right, where g is the optimal product function which is output by the bucket elimination algorithm, right? So all we have done is we have taken a particular bucket in the bucket elimination algorithm, and computed an upper bound, right, using this process of mini buckets over the function that is output by the exact algorithm, right? So h1 times h2, and these are two smaller functions, much smaller functions often in practice as compared to g. So this slide illustrates how to use the mini bucket idea to compute an upper bound on the MPE probability. Suppose our resource constraints, specifically let us say your RAM size, dictates that you can process functions having at most 3 variables and no more. Then instead of running the bucket elimination algorithm along the order C, S, T1 and T2, which has a width of 3 and thus will need to process functions having 4 variables and violate the constraints that are imposed by our RAM size, we can run instead the mini bucket algorithm by splitting each bucket which has more than 3 variables into smaller mini buckets such that the number of variables in each mini bucket is bounded by 3. Thus, in our running example, along the order C, S, T1 and T2, the bucket of C is the offending bucket. Therefore, what we will do is split the bucket into 2 mini buckets. The first mini bucket has 3 functions and contains 3 variables, C, S, and T1, while the second mini bucket has just 1 function and contains 3 variables, C, S, and T2. Since both mini buckets have just 3 variables in them, they satisfy our constraints, right? And the constraints, as I said before, are imposed by the RAM size. Next, what we do is we max out C independently from each mini bucket to yield 2 functions. The first function is defined over S and T1. So you can see the function psi of S and T1. And the second function is defined over S and T2. So if you see the function psi of S comma T2. It is guaranteed that based on the previous slide and the partitioning based upper bounding schemes, that the product of the 2 functions computed by the mini bucket approach is an upper bound on the function over S, T1 and T2 that would have been generated if we had run the bucket elimination algorithm. Okay, so what we are actually doing is we are upper bounding the function that will be output by each bucket using this mini bucket scheme. So once the mini buckets over C are processed, the remaining mini buckets satisfy our criteria that each bucket must have at most 3 variables in them. And now we can run our standard bucket elimination algorithm beyond C. So the approximations are only made at C, and beyond that, we are not going to make any approximations. Although remember that the functions that are sitting in the buckets that are below C are no longer so-called optimal functions, right? So the approximations, it will still be an approximation in the sense that we won't get the optimal assignment to S, T1 and T2 if we use those functions. Okay, so that's an important caveat that you should realize. So once this algorithm terminates, we will have an upper bound on the MPE probability, right? So once you sum out the last bucket, you will get this upper bound on the MPE probability. The scheme that I just presented belongs to a class of schemes called partition-based bounding schemes, right? Because what we are doing is we are taking a set of variables, right? Or I should say a set of functions in this case, and partitioning them into multiple mini buckets. This scheme can be further optimized using algorithms such as dual decomposition and linear programming. So what I've presented is essentially a vanilla mini bucket elimination algorithm, and this algorithm can be improved by using various optimization techniques as well as advances. For these advances, what I want you to do is refer you to the book by Kohler and Friedman, where these techniques are discussed in detail. So now that I've presented the algorithm for computing upper bounds using the mini bucket scheme, I come to my favorite question. What is the time and space complexity of mini bucket elimination? And the answer, since we have already learned about iterative joint graph propagation as well as other schemes, is straightforward. The complexity is exponential in the number of variables appearing in each mini bucket. Okay? So similar to IJGP or iterative joint graph Billy propagation, we can use the parameter I to control the number of variables in each mini bucket to yield an algorithm whose complexity can be controlled by a user-defined parameter. That parameter being I, where I will refer to the parameter as the I bound. As before, when I equals width plus 1, the algorithm will yield exact results along the order. If you recall, right, since we want to use this scheme as an upper bounding scheme in the branch and bound algorithm, we want higher quality upper bounds. And I bounds will help us achieve this objective of obtaining higher quality upper bounds in the following way. Typically, we observe, and actually this can also be proved, that if the I bound is higher, then the upper bound is better. Thus, when the I bound is high, the complexity will be higher. But what will happen is that we will explore far fewer nodes in the branch and bound algorithm, because the better upper bound, and in this case the smaller upper bound, will prune a large number of nodes. In general, and this is a rule of thumb, if you want to solve very hard problems, so for problems on which the MPE value is very hard to find, it is a good idea to use as high I bound as possible for computing your upper bounds. We can use the mini bucket approach in the branch and bound algorithm in a straightforward manner. Same idea as before. At each node where we need the upper bounds, we invoke the mini bucket algorithm with the assignment along the path from the node to the root as evidence. Again, recall that we prune nodes which have smaller upper bound than the best solution that we have found so far. Okay? So this approach is fairly straightforward. There are 2 points that I want to mention. The first point that I want to mention is that branch and bound is an anytime algorithm. What I mean is that if I stop the algorithm at a particular time before it terminates, the branch and bound algorithm can output its current solution. Okay? And this solution is guaranteed to improve over time. Right? And such algorithms are called as anytime algorithms. Right? So you stop it at any time, you have a solution. And as you give the algorithm more and more time, its solution quality improves. A final point that I want to mention is that instead of using OR search space, we can use the AND/OR search space, which will yield further reductions in computational complexity as well as the number of nodes explored. I'm not going to go over the details of how AND/OR search space can be used for performing MPE in the branch and bound context, but if you want to understand the details and see how well AND/OR search works as compared to OR search, I encourage you to read the PhD thesis by Radu Marinescu, who used to work in the same lab as me in Professor Rina Dekter's group at UC Irvine. And the link to the thesis is given on the slide. Let us switch from MPE inference now to map inference, which at a high level is generalization of MPE. The problem is harder because it is a max sum product problem and we cannot distribute max over sums. Therefore, we have to solve the problem in two stages. We first perform the sum product task and then we perform the max product task. From the point of view of bucket elimination, we divide the variables into two sets. Variables which we have to sum out, right? And we'll call those variables as non-map variables, and variables which we have to max out, and we'll call those variables as map variables. In bucket elimination, what we will do is we'll first run sum out based bucket elimination over the non-map variables, and once that is complete, we will run max out based bucket elimination over the map variables. To make things more concrete, let's say that the map variables are denoted by M and the evidence is denoted by E. When we sum out the non-map variables given evidence, we are effectively computing the marginal probability distribution over M and E. And remember that this distribution is going to be in a factored form. By maximizing out map variables M from this joint distribution, which is defined over capital M and small e, we are effectively solving an MPE problem over the resulting marginal, right, which is expressed in factored form. Although the bucket elimination algorithm, as I just described it, does not change much, there is one important distinction, right? And I want you to focus on this. There are huge implications in terms of computational complexity. Notice that we can use any order over the non-evidence variables when we are trying to compute probability of evidence. However, in the map inference task, we sum out first, right? And so we have to ensure that all the non-map variables are ordered before the map variables. If they are not, then since sums and maxes or sum out and max out operation does not distribute over products simultaneously, our algorithm will be incorrect. Okay? So that's the constraint we have. The constraint is that we have to ensure that all non-map variables are ordered before the map variables. Thus, the best we can do in terms of computational complexity for bucket elimination, when bucket elimination is used to solve the map problem, is no longer exponential in the tree width of the graphical model, but it is actually exponential in another quantity called constrained tree width, which searches over constrained orders in which the non-map variables are ordered before the map variables. And typically, since we are searching over constrained orders, the constrained tree width is going to be much higher as compared to the tree width of the graphical model. And this is a problem, right? Because computational complexity is exponential in tree width, and now instead of the computational complexity being exponential in tree width, now it's exponential in constrained tree width, which is a which in practice I should say is going to be much larger as compared to the tree width. So in this slide, what I'll try to do is I'll demonstrate what I just said about constrained tree width and tree width, right? So what I'll try to demonstrate is the implications on complexity because we are using constrained tree width instead of regular tree width. Consider the graphical model, or rather the Bayesian network that is given on the slide. You can verify that the tree width of the primal graph associated with the Bayesian network is true. For example, if we use the order which goes like y1 x1, y2 x3, y2 x2 I should say, y3 x3, y4 x4 and so on up to yn xn, and we compute the width along this order, we will see that the width is 2. And since this graph is not a tree, width of 2 implies that tree width equals 2. Okay? So now if you're interested in the MPE problem over the variables x1 to xn and y1 to yn, the problem can be solved in time that scales exponential in 3, since the tree width is 2, using an algorithm such as the bucket elimination algorithm. Unfortunately, the constraint tree width for this problem will be at least n rather than a constant if we want to find a map assignment over the variables y1 to yn. So here we have to sum out x1 to xn, okay, and then find an assignment to y1 to yn such that the probability is maximized. Okay, so since we are eliminating x1 to xn before y1 to yn, we will create a clique over y1 to yn, and you can verify this. No matter what order we use, we are going to have a clique over y1 to yn. Okay, thus computing MPE via bucket elimination, which I'm calling BE underscore MPE, will be exponential in 3, while computing map using bucket elimination, and I'm calling that algorithm as BE underscore map, will be exponential in order of n. Okay, so one is exponential in a constant and one is exponential in n, which is a variable. So you can see the huge gap in complexity. So this illustrates, and this is a pathological example, but this illustrates the difficulty with map inference. Even on graphs which are very simple, they look like trees. Okay, map inference becomes an extremely hard problem as compared to MPE inference. So in practice, and this is an active research area in the sense that because map inference is a hard problem, we need more specialized and advanced algorithms, right, rather than the algorithms that we are discussing in this class. It turns out that we can also use the branch and bound algorithm to solve the map problem. Here, we perform DFS search over the map variables and use the mini bucket version of the map algorithm to compute the upper bounds. Okay, so mini bucket version of the map algorithm, which I'm going to call MBE underscore map, is same as the mini bucket version of the map of the algorithm for solving the MPE task, which I'm going to call MBE underscore MPE. What is the difference between the two? The difference between the two is that in the map case, we have to order the map variables after the non-map variables. Okay, so non-map variables will be ordered before, and then come the map variables. Okay, the branch and bound algorithm remains the same. Of course, since the map problem is a much harder problem as compared to the MPE problem, the branch and bound algorithm will not perform as well as the algorithm that solves the MPE problem. Okay, because we are solving a much harder task. Okay, so we'll stop here today. I think this is approximately an hour-long lecture because there's no feedback and there are no questions. So I'll make sure that all my lectures are just 1 hour. And what you should do is, and what I encourage you to do, is post your questions on Piazza. Okay, and if the questions are interesting and they're relevant to the whole class, I will try to answer them via video rather than text. Otherwise, if there's a simple answer which does not require a video, I'll answer them via text. Okay, via text on Piazza, I mean. So I'll try to answer these questions by Thursday. So please post your questions before Thursday morning. Next class, what we'll do is we'll look into local search algorithms for solving map as well as the MPE task. Okay. So think of these local search algorithms as sampling style or hill climbing style algorithms, and we'll discuss them in the next class.